Anyway, let's get started. I'm just filling in time because we have nothing but a short weekend's gonna start early. Look at what I put on this board. I literally am tempting you to start your homework early. Can you believe the temptation I'm placing right here? I'm using pure words here, ready? Now, I want to refresh your memory. Up to now, every time we did normal distribution, it's always been x minus the mean in the numerator, right? Does that sound familiar? But now, we're doing proportions for the first time. But it's very much like the mean as far as the numerator is concerned. The left-hand side is always the proportion you're being asked to find the probability of. That number is your x if we were talking about the mean. The one you're being asked to find the probability of. The right-hand side is the proportion in the story that is expected, the historical proportion or the given proportion. In a story before today, it always was the mean. The mean was being described in some way, and that would be the right-hand number. But now it's the proportion. A proportion is a percentage, by the way. 0.72, 0.55. A proportion just means another word for percentage in decimal format for these calculations. That expected proportion that's on the right, here's the weird part. It's used in the denominator. So that number, the given expected proportions in 3 places. This denominator before today, what was it? It was the standard deviation over the square root of our sample size. That was called the standard error when we were using the mean. But now that we're on proportions, this is the standard error. The expected proportion, like point something, multiplied times 1 minus that expected proportion, the opposite of the expected proportion. And once those two are multiplied, then divided by the sample size. Then square root it. Here it is. This is what I didn't want to give away earlier. I'm going to give it away now. The number one mistake with proportions that I'm going to see on the final exam, and even though I'm emphasizing it right now as hard as I can, someone's still going to do it, just like I quiz 1 and quiz 2 when I emphasize it. Number one mistake is the square root is over the whole thing. You got to do all of this before you square root. A lot of students will mix up the square root only being over the numerator part of this. It's not. You don't do these multiply, then square root, then divide. You multiply these, then divide, then square root last. That's the mistake I don't want you to make. Square root last on the denominator. Then after you square root, you divide it into the numerator. So you do the numerator, and you've got to do the full denominator, then divide it in. You just found z. That's how you find z. Now that you found z, it's just like we've been doing every other week. You wouldn't look at a z chart though. Oh, I gotta put it up here. I almost forgot. We're using this norm S. I gotta make it as big as I can so you guys don't forget. S DIST, and here you're putting in that z you just calculated. We're not using the z-chart. Z-chart's not going to be on the final exam. Z-chart's not allowed. No reason for you to get it. You can get it out and have it while you're taking the final exam to maybe confirm that you're doing it right if you feel comfortable with the z-chart. But there's no reason for it because you've got to give me this norm S distribution equation on the final exam. This is replacing the z-chart. This is what I got to see. If you're asked to do this manually, this has to go with it. Proportions or mean, whichever ones. You got both of these involved. Just like all your A's on the homework you just handed in. I'm giving you way too much information. Let's look at the instructions. Whoa, hey, oh, what is that? No, I forgot. Now I want to point something out about the upcoming homework. It has B's, just like this week's homework did. And I want to point out, we're using normal distribution again, just like we have in the homework you just handed in. But the first number, let me start with the first number, is what is that called? The proportion, excuse me. The proportion being asked to find the probability about. The proportion being asked to find the probability of is the first number. The second number is the expected proportion, the history proportion, the historical proportion, the given proportion. There it is. The third number is the standard error. But because this is proportions, That's the standard error, not that standard error you just did on your homework. That's standard error right there. The square root, SQ, RT, parenthesis. Should I make up a number here so I can show you how it's going to look? The square root of this whole thing is going to be, pretend like the expected proportion is 0.72. 0.72, 0.72. You got to put the star on Excel for multiplied, parenthesis, 1 minus 0.72, parenthesis, divided by sample size, call it 50, parenthesis. The square root has to be on the outside of these last two parentheses. In the middle is the expected proportion times 1 minus the expected proportion divided by the sample size. Many people will accidentally leave that asterisk off, but on your final exam, you won't be able to get an answer if you leave it off, so you'll end up correcting yourself. But on the homework, I bet you some of you will leave that off, but don't. This doesn't assume multiply if you put it next to each other. You got to include the asterisk in Excel. Come here, come here, come here. Just checking. All right. Let's get some boring stuff out of the way. I'm not going there, not going there. I'm calling an audible. I'm going straight down to slide 3. Anybody keeping track? Now, notice there's 2 chapter 7 PowerPoints. I almost forgot to point that out to you. Last week was chapter 7 PowerPoint. This week is chapter 7B PowerPoint. Make sure you realize there's 2 of them. We're on the B today for the first time. A couple of definitions that I will guarantee there's at least one of these on your final exam. I can't remember which one. I haven't read it yet, but I always grab one of these. So the first one I want to point out is from slide 3. It's about bias. This is about sampling. Remember, the sampling I showed you that I talked about where we get random numbers by using Excel with the RAM between, and then we had the 900 applications and we numbered all the applications and we drew them out based on the numbers we got. That was just general randomness. Here are some of the other ways randomness is done and other concerns in the technique you use to have a random sampling done. One is called bias. That's the number one concern when it comes to random sampling, that there might be bias in the sampling technique. This says the tendency of sample statistic to systematically over or underestimate the population parameter. That somehow there is bias involved. Here's an example of bias. This is back in 1936. This newspaper went ahead and published a newspaper that said Alf Landon won the election over Franklin D. Roosevelt in 1936. So they went back and said, how could this have happened? How could this newspaper have done that? And they said, we went ahead and posted in our newspaper what our sampling from our survey told us. Then they said, okay, how did you get your sample? Well, we asked readers of our particular newspaper to answer the question, who did you vote for president? And they said, okay, there's the bias. If you're only asking people who read your newspaper, you're only going to get responses from people who happen to read your newspaper. Where there's people who, most of the people who voted in a national election do not read your newspaper. So you left out a whole bunch of opinions that had nothing to do with the people that you were getting this from. So that was called bias. They should have taken the survey from all different parts of the nation, from all different people, whether they read this particular newspaper or not. And that's what they learned about that in 1936. That was a huge embarrassment for this newspaper. I don't even know if they ever exist. Literary Digest? Literary Digest. I don't even know if they exist. Oh, they also said they committed selection bias by randomly sampling their own subscriber member list only. In addition, with only 24% response rate. They're saying out of everybody they sent this survey out to, only 24% responded to it. And when you only have, so they were using phone back in 1936. So only 24% is considered biased because there were 76% who says none of your business or I don't have time for this. And those who felt so strongly about it could have been all for one candidate. So you almost have to use a phone to try to get that kind of bias out of there, to try to get everybody to answer, who did you vote for? We're doing a survey so we can try to predict who's going to win the election. Anyway, so that's what bias is. Next, These are two different types of bias. One is called selection bias, non-response bias. The selection bias, great example again, is that Literary Digest committed selection bias because they excluded a large portion of the population. Because there's a huge portion of the population that does not read their magazine, would never have gotten their survey to be asked that question, who did you vote for president? So that was called selection bias. Non-response bias is where, because they did it by mail, and such a huge majority of people never responded, and only a small minority responded, 24% is all that responded, that's called a non-response bias. That all those people who didn't respond could have maybe changed the results of that survey had they responded. So you gotta change the process of doing the survey when you have such a low response. That's called non-response bias. How would that be asked on a question? I don't know. Literary Digest did a survey to try to see who won the presidency. They only got a 24% response. What kind of bias would that be? Here are your 5 choices. Selection bias, non-response bias, da-da-da bias, da-da-da bias. Multiple choice. Just give you an idea of what I'm preparing you for. What percent of your grades final exam, by the way? Is it 20? No, it's gotta be more than 20 because quiz 2 was 20, wasn't it? So it's like a 4th year grade, like 25. It's a big deal. When is it? Right here, is this it? Tuesday, the 25th at 11:30, is that correct? Not 11. I'd get here at 11 anyway. 11:30. Don't forget, sign C, have your stuff on a flash drive, or get here early enough to get everything off a canvas. Everything's the same. Open materials, open book, notes, digital. All right, so now, where are we on? 6. Let's take a break from this. Let's take a break. All right, so now, what other things might be on this exam that you gotta have before we get to a little interesting stuff? Would be, I'm on slide 6 on the 7B, simple random sample. No, I'm not on slide 6. We already talked about simple random sample. We know what that is. But here, stratified random sampling. Stratified is when you break the population into these groups called stratas. Break the population into groups, and then you purposely are getting samples from each group based on what size that sample is within the population. So let me give you an example. I gotta make sure I say this right, because this is very close to cluster. And the difference, cluster sampling is where the groups are broken up by, in my experience, it's always been geographical. This one's in this group's in this region, this sample came from this region, this sample came from this region. That's called cluster sampling. Stratified sampling is when the groups are broken up into different categories, such as age groups would be a good example. Here are the ones, this samples from those in their 20s, this samples from those in their 30s, those in their 40s. In both cluster and stratified, the groups, the subgroups, have to be mutually exclusive from each other. Now, I want to make sure you understand what that means. That means there's no possibility of an item in one group that could also be in another group. That's not possible. In both stratified and cluster, each group has to be mutually exclusive from the other one. So, let me talk about stratified again. The groups are those in their 20s, those in their 30s, those in their 40s, right? If somebody's in their 30s, there's no way they can be in the group in their 40s because they're not in their 40s. Each group is mutually exclusive. Now let me go with cluster. Those in the south region, and the boundaries are clear. There's no way someone can live in the south region and live in the east region group at the same time. It's either one or the other. That's what makes them also mutually exclusive. Even though we're talking about something totally different, not necessarily ethnicity or age, we're talking about geographical location or something. That's the difference between cluster and stratified. Now, let me get to this part. Cluster, preferred when, cluster, the advantage of doing cluster sampling, which is geographical part, is it's a lot less expensive to get the sampling done using cluster. Where stratified, I'm trying to remember what's the advantage here, preferred when the objective is to increase precision. Now the reason stratified increases precision is because, you ready? If I said to you, the groups, we're gonna get samples from people in their 20s, 30s, 40s, 50s, and 60s, and our sample size is gonna be 100, but here's the breakdown. This is what makes it more precise with stratified. The breakdown would be, okay, the population these samples are coming out of, what percent are in their 20s? What percent are in their 30s? That's the same percent of the 100 we're gonna pull out of the group that are in their 20s. So if the population in the population has 30% of people in their 20s, then our sample of 100, 30 of them have to come out from people in their 20s. If the population has 10% of people in their 60s, then our sample of 100 has to have 10 of them coming from a group of people in their 60s. So the sample matches the population. That's what makes it so precise. So that's what the difference between stratified and clustered. All right, what we got? We got one more here. Slide. No, that was it. 10. That's right. Now we have another boring subject, kind of, but let's get to the fun stuff. Let's get to the fun stuff. I want to make sure you could get started on your homework if you wanted to. I want to make sure you understand proportions. It feels like the air conditioning's on here. It feels good to me, but I'm sure you guys are cold. Anybody? Is it cold in here? Is it?
Yeah.
I love it.
That's cool.
It's the first day I didn't have to have my fan. You remember this? I've mentioned this like 3 times now. You're the admissions director. You've got to go to this meeting. Does this sound familiar? You've got to go to this meeting. We've accepted 900 applications, but we haven't entered them into the system yet. You're being asked to bring 2 numbers to this meeting. One was the average SAT score. We talked about that on Tuesday. But what we didn't talk about is you're also asked to bring the percent that said, yes, I want to live in on-campus housing. That's a proportion. That's what you're being introduced to today. That's what everything's changing today. It says you're bringing the individual scholastic SAT score and whether or not the individual desires on-campus housing. We got to get that percent. So we took a sample of 30. We don't have these 900 applications in the system. We took a sample of 30. Remember this? Here's our 30. There they are. Blah 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 blah. There's our 30. Here they are. The first student said, yes, I want to live on campus. Second one said yes. Third one said no. We counted all the yeses, divided by 30 to get a percentage of those who said yes. That's called a proportion. Then we reported that proportion at the meeting. The housing director said, oh, let's see what we reported, by the way. We reported 68%. Out of the 30, 20 of them said yes, I want to live on campus housing. But we only did 30. But at least the housing director now has at least a little bit of an idea saying, okay, well, if we have 900 new freshmen coming in, 900 times that 0.68 gives me an idea then how many to expect, so I know how many rooms to prepare, how many beds are needed, blah, 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 blah. Right? That's a proportion. That's what everything is changing right now. So let's see how close we were. The sample proportion was 0.68. The population proportion was 0.72. That's not bad. That wasn't far off. Now, let's turn this into an exam question. Hey, now that we have all the applications into the system, all 900, 72% of them said, yes, I want to live on campus housing. What's the probability that we walked into that meeting with a sample of 30 and could have said, hey, the proportion that said yes, they want to live on campus is 65% or less. That's significantly below. Matter of fact, 65% is how far below? 72, 65, that's 7 below. That'd be 7% below what the actual is. That's pretty far off. What's the odds of us walking in that meeting and we said 65% or less? Key words, or less, or less, or less. All right, let's go. Let's do this. What number is the proportion being asked the probability of? What number? 0.65. 0.65. What's the probability that we could have walked in that meeting with a 0.65 from our sample of 30 or less? What is the expected proportion that we now know? 7.2. What is the expected proportion in the denominator right here? 0.72. What's the, hang on. There we go. What's the expected proportion in the denominator right here? 0.72. What is the sample size? How many?
900.
How many?
You said 900.
30.
Was it?
It was 30 in our sample size. Let me go
No,
back.
no, no, no.
Hang on, I just want to make sure you guys know where I'm coming from here. Right here, 1 through 30. Right there they are, the 30 of them. And then right here, we
30.
will continue to draw random numbers until we have selected 30 applications for our sample. So there's the sample size. And from there, we would calculate the probability. I don't want to calculate all that, but that would get our Z, and whatever that Z is, we put right there. My question for you is, would I put a 1 minus in front, yes or no?
No.
No, because I said, what's the probability that our sample could have given us a 65% or less? That we would have done harm to our housing director. We walk in there with a 65 and the reality is 72. The housing director would go, oh my God, I'm not prepared. I expected far less out of these 900 students than what you told me at the meeting. So whatever that is, we plug in here and we get that percentage, but here's the easy way to solve this. Using norm distribution. Let's get an Excel spreadsheet open. We still on? We're still here. Here we go. Equals NORMDIST. Should I put a 1 minus in front? Good call. Parenthesis, what's my first proportion here? This is all in decimals now because we're using proportions. What's my first proportion?
65.
65, because it's whatever the proportion that you're being asked the probability of. Just like every week before this was the X was whatever number you're being asked the probability of. So 0.65, comma, what's my next number?
0.0.
72, exactly, the proportion that we expected, that we now know about the population. 0.72, comma, here it is. This is the standard error. I'm going to type it in like I just taught you right here. SQRT, parenthesis, what number? 72 it is, 0.72, asterisk, parenthesis, 1 minus 0.72, parenthesis, we're not done, divided by what?
30.
Very good, 30. Now what?
1.
No, I gotta have a parenthesis. I gotta have that ending parenthesis or that square root won't work. It's that square root, everything after the square root's gotta be in the 2 parentheses. So right before that beginning 0.72 and after that 30, comma, now the 1. Always a 1 with normal distribution, right? Here we go. When I hit this, this is the probability that we could have walked into that meeting because we only took a sample of 30 and reported 0.65, 65% said yes, they want to live in student housing or less, which means we would have blown it. That would have been kind of misleading for the housing director, which may not have enough rooms prepared because it ended up so low. This is the risk we had of blowing it. Here we go. Almost 20%. There was almost a 20% chance that we could have walked in with much too low of a number and put the housing director a lot of stress and pressure on that person. Everybody see how I did that? That's a perfect final exam question. You would have to give me that equation in full with the equal sign and everything. Some of you are still forgetting the equal sign, by the way, on that in-class assignment. Some of you are still forgetting the equal sign. And you have to give me the result. How are we doing? Let me keep looking here. We still got this over here. We still got this over here. This over here. We getting hungry yet? How many more times do we meet after this?
5.
5. That's it. Only 5 more times we get to hang out. Let's make it one. Let's get to this other stuff now. Hang on a minute. Let me close this. Here we go. Go in here. We're going to go slide. I forgot. 23. Do you happen to have this one? Here it is. Here it is. Where is it? Right there. Central limit theorem. There it is. One of the most important things for you to learn this semester is that this exists and that it works and that we're doing problems related to it right now. What we're doing right here and what we did last week, that was homeworks, are all based on the central limit theorem and how these probabilities work. And it basically says, no matter what kind of population you have, it could be a Poisson population, it could be exponential, it could be a uniform population, that if you take a sample size large enough, it forms a normal bell curve. Let me show you. like this. See that bell curve on the left? I'm colorblind, but I think that's a blue line straight across the bottom. Is that true? Because I do see blue. Is that blue?
Yes.
That straight line is a uniform distribution. Remember the salad? The salad can weigh anywhere from 8.5 ounces to 4.5 ounces, something like that, uniformly distributed. That's right there. But if we start sampling, let's say, okay, there's 1,000 people or 100 people out there with salad. Let's just go weigh 30 of them real quick. We'll weigh 30 of them. We're forming a bell curve around the mean of salad weights. And now we just took a uniform distribution and turned it into a normal distribution because we sampled it. That's what's going on. That's what the central limit theory says. It says no matter what kind of distribution the population is, if the sample's big enough, it will surround some kind of central number. When a mean, when you're talking about numbers, not proportions, but numbers, it will form around the mean. That bell curve forms around the mean, but proportions, let me get to proportion. It's almost the same. You take a sample out and it forms a bell curve around the center of the proportion, no matter how the proportion is. On the left, that blue curve, that's called, that tail is longer out to our right. So that'd be skewed to the right. Wherever the tail is longer is called skewed. It's a very common phrase in statistics, could be on your final. Skewed to the left, skewed to the right is all based on where the extension of the tail is longer. That's where the skew is. So this would be skewed to the right if you look at the blue curve. But then when you sample it, it forms a normal bell curve. So now you can use normal distribution to find probabilities. Same on the right. We did a sample of 100 and it formed a bell curve with proportions. So these are proportions, same thing. Now here's the rules to make central limit theorem really work. I want to go to first mean. This has to do with last week. The key words here for this to work is, the general rule is your sample size, that's what that small n is, must be greater than or equal to 30 if you're taking a sample around a mean. This is not proportion, this is last week. If you're doing a sample around a mean, the rule of thumb is that it should be 30 or larger. That's always been the rule of thumb in statistics. Now, with proportions, the rule of thumb is slightly different. For the central limit theorem to work, the rule of thumb is that you take the sample size and you multiply it by the expected proportion, and that should be greater than or equal to 5. Or you take n, you have to do both of these to test it, and you take the opposite of that proportion times the sample size, and that too has to be greater than or equal to 5. Let me make sure you understand this. Here's our sample size of 30, here's our expected portion of 72. My question is this sample size large enough, according to this equation, these two equations, that I could apply the central limit theorem to that question? What's the probability? We walked in with reporting housing, students who said, yes, I'm gonna go to housing at 65% or less. What's the probability of doing that? Could we use, will this be a correct formula to use based on that question right there? Now, I wanna tell you something on the final exam. You do not have to test whether you can use this central limit theorem. You're gonna be doing these as if you know that it meets this criteria, that the sample sizes will be large enough, greater than 5. Whether the question's about a mean or a proportion, you don't need to test that. I'm making sure that you will have the information that the central limit theorem will work. But I do just wanna make sure you're aware of it for a multiple choice question possibly. Here's our example, let's test it right now. The number in our sample was 30 times the given proportion, which was 0.72. Someone do that for me and tell me what you get. This one would be 30 times 1 minus 0.72, and tell me what you get. So the opposite of 72% would be 28% of 30. What is 72% of 30, somebody? 21.6. 21.6, which is greater than or equal to 5. So we're okay with that test. 28% of 30 is what number?
8.4.
8 point what?
4.
4, which is also greater than or equal to 5. Both tests work. That means we could easily apply the central limit theorem, and we could find the probability of us walking into that room reporting 65% or less. That's what the central limit theorem means. I think, I'm almost sure you're gonna have some kind of question related to the central limit theorem on your final exam, because it's such an important subject. One of the most important subjects we've learned this whole semester is this central limit theorem. And this will come up in 302. This is one of the things we were asked by 302 to make sure you understand, is that the central limit theorem, as long as the sample size is large enough, it applies. That's the key words. How we doing? We're running out of fun stuff and boring stuff. We're just running out of stuff, period.